Today's lesson is a continuation of section 10.1, graphing quadratic equations, y equals x squared or ax squared plus c. Again, the first lesson we started talking about graphing quadratic equations. We started comparing equations to the parent quadratic equation, and didn't have time in the last lesson. Just wanted to show you a little bit, again, what these should start to look like when you're graphing, and graphing these by hand as we were doing here some of the first days. I don't expect things to be perfect when you're graphing them, but just to show you, here's what parabolas should start to look like a nice smooth curve on Desmos here, using this to help me. I've got the parent function there in black. Again, just notice how it should be kind of like a U shape. It should look symmetrical. Try not to make them look like V's, as I always see every year. Try to make them more like a U shape, like a smooth curve. But here's what parabolas should start to look like. And even as I zoom out, I can find more points, but obviously increasing in both directions, going on and on. And we just notice that there's that symmetry, and we'll talk about that a little more today too, how this left side looks like the right side. Nice thing on Desmos too, we talked about the vertex yesterday, that lowest point. And Desmos, again, you can click right on that vertex and find out what that is typically on your parabola, no matter where it is on the graph. Kind of a neat feature of Desmos. But again, showing you what some of the shapes of these should start to look like. So here, this next one, y equals x squared minus 4. We talked about this being like it's just like the parent function, correct? Except it's a translation. So minus 4, so down 4 from the parent function. Should look about the same, but just be lower. And if you take a look at it, and we kind of took a side by side or tried to overlap, and we would see it's the exact same graph, but the blue one, just notice, is 4 points lower. Especially that vertex, you can really see it as 4 points lower than the parent function. Even any particular point that you look at, even if you look at like the point 1, 1, which is right here on the parent function, well then when you put in 1 in the function we have now, it's just 4 spots lower. So it's 1, negative 3, if I can click right on it. 1, 1, negative 3. It's just 4 spots lower exactly. So all points in the parent function, it's the same as those, except just shifted 4 spots down, hence the negative 4 in the equation. So there's the translation. Again, notice the nice smooth curve of it as well. This next one here, y equals 2x squared. So we talk about this first number, that leading coefficient. It's kind of like the slope when we had linears. For a linear equation, this would make a steeper slope. Well, same thing here for the parabola. It makes a steeper parabola, and we call it a vertical stretch is what we call it. But notice how the green one actually is inside of the parent function, because it's all like both lines in both directions are steeper. And if I even take y equals 5x squared, again, this is even a bigger number than 2, so guess what? It's going to be even steeper. The orange graph is even, it looks like skinnier on the graph. That's kind of what it looks like. What we call it is a vertical stretch, because all the points are again higher or steeper, just like a graph about linear gets steeper. Same thing here. The parabola itself is steeper, and so all the points that would be on the parent function are just higher on the graph. When I put in 1 to the parent function, I get 1. When I put in 1 into my orange function, I get 5. So it's stretched vertically upwards. So we call that a vertical stretch. Both of these would be. And obviously, again, the bigger the number, the steeper the graph. So then going the opposite direction, this next one, if I have 1/2 x squared, that leading coefficient is something between 0 and 1, well then again, almost it's like the graph gets wider. We call that a vertical shrink, is what we call it. Because in this case, plugging in 1 to the parent function, I get 1. But plugging in 1 to this function, I get 0.5. I get something that's closer to the x-axis. This 1/2 makes all the points shrink down closer to the x-axis. And so vertically, they come down. So they call it a vertical shrink. And so the way you see it on the graph, though, is it looks wider. If I plug in y equals 1/2 x squared, or even if I make up a new one here just kind of on the spot, y equals, how about 1/4? It will be even wider, kind of, again, the points will be lower than the parent and even lower than the purple one I have up there. So there's a vertical shrink when I see some number here between 0 and 1. It's fractions, decimals, things like that, numbers between 0 and 1. And then the last one I have up here, last example, is y equals negative x squared. We talked about this being the reflection over the x-axis. So there's the parent function, and y equals negative x squared. One just flips it over the x-axis, and all my coordinates then are negative. As opposed to having 1, 1, now I have 1, negative 1. So those were our transformations in this. Again, I wanted you to see some smooth curves and what it should start to look like when you're graphing. Not that when you're graphing by hand, it's going to be perfect, but should start to look, try to make it as close as you can to making like a nice smooth curve, like a parabola should look. And then from the previous lesson, again, we talked about a couple important points, or one particular point on the parabola that's very worthwhile, or usually ends up being solutions to our problems or word problems or things like that. The vertex, as we call it, is that highest or lowest point that's on the parabola, that point where the graph starts to turn around and go the other direction. Going along with that, maybe you saw it on the tables, and you should see this on your graph, and we kind of pointed it on your graphs, and we pointed it out on Desmos as well. There's also another important thing that we'll talk about with parabolas called the axis of symmetry. And it's just like it sounds. We know what the x and y axes are, just horizontal and vertical lines that, again, can define where we are on the graph, but they're just straight lines up or down and left and right. Well, the axis of symmetry for a parabola, symmetry means looks the same, right? We started talking yesterday about how the parabolas look the same on the left as they do the right, and how there should be kind of that overlap. We saw that in the tables, and we also see that on the graphs. So the axis of symmetry is just a line that we can draw for a parabola, and we'll find out this will be very important as we go forward graphing. But it's a vertical line in this case, since the parabolas we have are vertical, upwards or downwards for U shapes, that divides the parabola into two halves, and it goes through the vertex. So I've got some graphs down here, and you should draw in the axis of symmetry and also identify what the vertex is, which I think we can do. We started doing some of that yesterday. If you look at this first graph that I've got up here, and I know you have this slide, the pictures might be a little in different order possibly, but here's the three pictures we all still should have. Here's the vertex for this first one that I've got, where the vertex actually is on the y-axis. It looks like the vertex for this one, again labeled capital V, is 0, -4. And the axis of symmetry would be this line. In this case, it is like the y-axis. I'm going to use it as a dashed line here to kind of show that. But it would be that line. And notice that, again, the parabola looks the same on the left as it does the right. That's always what happens for parabolas for this type of shape. That equation, we do have an equation for that line, the axis of symmetry. In this case, that would be x equals 0. It's along the x, it's a point along the x-axis. I haven't moved left or right. It's a straight vertical line. It is actually the y-axis, and that is the equation for the y-axis. X equals 0. We haven't moved left or right at all. Okay, it's straight up and down, but we haven't moved left or right for any of the points that go along this line. So x equals 0. In that case, that would be the axis of symmetry. I'll just kind of give you a little hint going forward for the next ones. I bet you can help pick it out. Our point was 0, -4. Our x-coordinate was 0, and we know the axis of symmetry was x equals 0. Okay. I'll go to the one that's on the top right here for my slide. Again, it may be in a different place for you, but this one that looks like the vertex is right here at the point 2, 2. So take a look at that graph. Vertex is at 2, 2. Well, again, you can imagine, and in the future we'll start drawing this in. We can start today, drawing in the axis of symmetry for our graphs. In the future, it'll be even more important to kind of start seeing some connections for graphing, and so we don't have to make tables. There's a way we can use this to graph. But there's the axis of symmetry, and the equation for this would be x equals 2 for this one. Because all the points along this line would just be 2 to the right, and then it's just straight up and down. So here's the axis of symmetry. You can abbreviate it. It's A period, S period. So axis of symmetry, x equals 2, and the vertex itself in this case is 2, 2. And then that last one I've got, that last graph for you, wherever the third one happens to be, first maybe identifying the vertexes. In this case, looks like it's right down here, and it's in between grid lines. So I'm going to say the vertex, to me, that looks like it's -1.5, and then -11, down 11 from the origin. So -1.5, -11. So what would be the axis of symmetry for this one? X equals -1.5. That line, the graph of that line would be the axis of symmetry. Since I've got Desmos up, I'll show one more example with that too, and then I can show you on Desmos how you'd put the axis of symmetry in there as well. I've just kind of made an equation here quick that's a quadratic, so y equals 2x² minus 8x plus 3. And notice, yep, I've got a U shape here. And my vertex I can just kind of click on in this case, which is 2, -5. The axis of symmetry, the vertical line that would split that parabola in half and make the left side equal to the right side, would be x equals 2. And so you can see that, yep, it splits it right down the middle. And I know typically when I do it, I do a dashed line, so you can even do that in Desmos as well. and just kind of show that. But we'll do some things soon with Desmos, so we'll be putting this in as well. But there's how I can see the axis symmetry, and I can see that, yep, what do you know, symmetrical on each side, left and right. So in that previous page, we kind of started talking about this already and used Desmos to kind of talk about it, so I won't spend as much time on this slide, but at least not on the top part here, it says what makes a parabola wider or translate or face it upside down. We kind of showed that on Desmos, the different numbers that do that. It's that value of A. It's the value of A here. If it's greater than 1, it's a stretch. If it's between 0 and 1, it's a shrink. If it's negative, it's a reflection. Or C can be what makes it translate. Again, what I want you to be able to get to the point of doing, and today we'll still make tables when we're graphing these equations, but pretty soon we'll be just using these facts or knowing by looking at an equation. I want you to be able to tell what you should expect to see when you're going to graph a parabola. By looking at the equation, you should know, oh, it's going to be a reflection. Oh, it's going to be translated up or down. So when you're looking at, let's say, these three equations right here, when you're graphing ones today, what I'd like you to try to do first before you start graphing is telling which types of transformations are you going to see for this graph. So for example, the red one I've got up there, y equals x squared minus 5. So taking a look at that, it's like the parent function, except it's minus 5, right? The y-intercept or the vertex would be 0, negative 5. So it'd be the parent, but it'd be down 5 spots. So that would be a translation. So when you're doing problems today, I want you to try to put that first, if you can. Try to put down what the transformation will be first, and then go ahead and make a table and graph and see that that is what happened in your graph too. It's a translation in this case. Take a look at the blue one. Y equals 2x squared. So from what we learned the other day, since that A, that leading coefficient, is bigger than 1, this should be a stretch. So today, let's say this is your first problem. That's your equation, y equals 2x squared. Well, the first thing you're going to do is for number, let's say problem number 1, you're going to write down stretch. And then you'll go ahead and make a table. You'll try to put in the points and then try to make a graph and see that hopefully it does look like a stretch. It should look steeper than the parent function. Like again, it kind of look like it's skinnier is what we think, but they call it a stretch. So that's what we'll use is a stretch of the parent function. Good, and that last one, now the green one, y equals negative 3x squared. So same thing there. And then as we notice, it can be a combination of the transformations too. Since that one is negative, it will be a reflection. And 3, I know it's negative 3, but 3 itself, the absolute value of that, is a number bigger than 1. So this will be a stretch reflection. It should appear steeper, or again, you can think skinnier than the parent function, but it should also be a reflection facing downward. And then when you graph, you should see that happen. That makes you a better grapher. It helps you understand how these things fit together by looking at the numbers and knowing what to expect before you put pencil to paper. So this last slide, going that same direction off of that same idea, you should also be able to do this for me for an equation as well. When we talk about these 4 transformations, if I give you some of the transformations, you should be able to make an equation that would do that compared to the parent function. So like for example, here are my 4 transformations, and right now, like on your notes, I'm just going to pick out a situation. Let's say I want you to make, compared to the parent function, I want you to make an equation that would be a stretch and a reflection. So you make one right now. Pause the video if you need. But compared to the parent function, what would be an equation that would be a stretch and a reflection? And I'll go ahead and put one possible answer. As you know, there could be many possible answers, but y equals, well, reflection means it would have to be negative, and the stretch part means it has to be some number bigger than 1, or at least like the absolute value of it would have to be bigger than 1. So I could say something like y equals negative 5x squared. And again, you could have some different answer, but definitely you should have a negative, and definitely you should have a number greater than 1. So trying some other situations out. Right now I want you to try to make equations for these. If I tell you I want, compared to the parent function, I want an equation that would be a reflection and a translation compared to the parent function. What would that have to look like? Or how about if I wanted a stretch and I wanted a translation as well? Or how about a last one? How about if it's a shrink, reflection, and a translation? By using those combinations, you should be able to figure out numbers that would make that work. Pause the video if you need right now, but otherwise try that out. Try to jot down equations that would fit each of those three situations. See if you can do it, and I'll put them down here as possible answers in just a second. So this first one that I've got here, reflection translation, y equals, well, just to make it a reflection, not a shrink or a stretch or anything, but just a reflection, that means I have to have negative x squared. That'll make it reflect over the x-axis, make it face downward as a parabola. And a translation means that I need to have some kind of constant here, like negative x squared plus 2. There would be a reflection translation. For a stretch translation, stretch means I have to have some a that's bigger than 1. So again, I can have something like y equals 3, or even about 30. Okay, 30 x squared. And again, for a translation, I just have to have some constant on the end. So maybe let's say 30 x squared minus 1. That would be a very, very steep parabola. But it'd also be down 1 from the parent function. So and the y-intercept would be 0, negative 1. So there you go. Y equals 30x squared minus 1. And how about this last one? A combination of all three of those things: a shrink, a reflection, and a translation. Okay, well, I can take care of the reflection right away. That just means I have to have a negative here. A shrink means I need some number between 0 and 1. And so usually I know we've been using fractions a lot, but I can use a decimal too. Let's say, how about just something like 0.2 x squared. That's a number between 0 and 1. And I made it negative to make the reflection part. So y equals negative 0.2 x squared. And then again, translation, maybe something like plus 7. So there are three possible answers. Again, your answers could be different. But as long as you're doing those kind of things, then you've made three correct equations for those situations. Last thing here, this last slide isn't really any more notes. It's just things that go along with this particular assignment. And in case you're doing it without me there, or you're watching the lesson online here, just things I want you to note. Here's the assignment that goes with this lesson, that page 633, 24 to 37, 41, 42. 24 to 32, kind of like I talked about in the slides there. The first thing I want you to try to do, you're going to be graphing those parabolas, graphing those equations. And first, I want you to try to write down the transformation. So write down, well, just looking at them. And you can do all of them right in a row first and start off by doing that and then graph after that. But first, just try to write down, is it a stretch? Is it a shrink? Is it a translation? Is it a combination of those things? Just first write that down for each one. You should know what to expect before graphing. So write those down first, if you can. Then make a table that has five points, and then label the vertex. I know we talked about axis of symmetry, but even just labeling the vertex at that point, we'll get to axis of symmetry more in the future, but label those things and then make your graph. That last one, number 42, just quickly note, just a reminder, there's our vertical motion equation, so you'll use that for number 42. That may be helpful to remember what's going to happen in that problem. And then 41, just know that you'll make some kind of parabola for the graph that it's given you. It may help to take a big piece of graph paper and to be able to graph it out and make it look correct and give it some idea what they're expecting from you. Just a hint that when you make a graph, you want to plug in numbers. Use a table, I would say, to put in some numbers and put in these kind of numbers: 5, 10, 15, 20, 25. Go by fives, and then that should give you a little better idea of what the graph should look. It should be kind of like a parabola shape, but using those numbers will give you better results and will make your graph look like something you can actually interpret.